In my previous video I flagged up a fault I'd found with the motor out of this MADAS calculator that I'm in the process of restoring. It's a very old mechanical calculator, it's over 100 years old, but it's a motor driven unit, and the problem I was having was leakage from the rotor of the drive motor. But it's very strange because the leakage was far worse in one polarity than the other. So if I passed DC current through the rotor in one direction, there was a lot of leakage from the commutator to the motor shaft. But if I reversed the current, there was almost no leakage at all. And I've been messing about with this now for about a day, trying to figure out what's going on. It seems most likely there's some form of corrosion somewhere inside the rotor. And so I've been tinkering with this. I don't really know what the material is they've used to insulate this. It's kind of a tarry substance, but normal solvents don't seem to dissolve it. That's the solvents I normally use for dissolving tar. It does melt when it gets hot, but I've got to be fairly careful because I think it's what the commutator's bedded down in, so I can't get it too hot or the entire commutator will start to disintegrate. But obviously I want to try and recover this motor. It's incredibly rare and the chances of finding a replacement are very slim. I could of course put a fake motor inside and it would look the same, but really what I'd like to do is get it fully functional. So what I've been doing is trying to figure out exactly where the leakage is coming from in the motor itself. And looking around and trying various things, it seems that the leakage is mostly coming from some of the packing materials they've used for the basically holding the coils in place. There'll be some underneath as well, which is unfortunate, I can't get to that. But I've taken out the top infills. If you're familiar with motors, you know these are what are slid into the slots in the rotor once the coils have been put in to hold the coils in place. I don't know what these are made from, but when they get hot they start to conduct, and it looks like there's some sort of weird corrosion built up on the surface of them, and it's the contact point between that and the steel of the rotor that seems to be causing the issue. So I tried various things trying to dissolve that layer, and what seemed to be working is alternately heating, cooling and immersing in acetone, drying and then immersing in denatured alcohol, drying, heating and then just repeating the process over and over again. What I've got now on test, you can see I've got some wire wrapped around the commutator. Be careful not to touch this, and attached to the shaft I've got another clip. I'm just going to move the camera. So these are attached to a couple of the Ryden power supplies, and they're both set to around 60 volts and they're in series. So I've got about 120 volts across the rotor. That's been fed through a current meter, and if we look up you can see that we're drawing just under 0.2 milliamps. So what I'll do is heat up the rotor with the hot air gun. And when I first started doing this, the cold leakage was about 7.5 milliamps, but when I heated it, it shot straight up to over 80 milliamps. And I could hear some crackling and buzzing within the rotor. It wasn't moisture. This thing's been in an oven for several days at about 80 degrees to try and make sure it wasn't just moisture that got in. But I'll start heating this up. Be a bit of noise I'm afraid, but I'll just heat it for a few seconds, and if you watch the current on the meter, okay, when I first started doing this, after about 5 or 10 seconds the current had gone up to way in excess of 70 milliamps, and here we've only gone up by a fraction of a milliamp, and it goes down lower each time. So I think the conductive layer is starting to break down. Just going to move the camera back down again so you can see the rotor. So what I intend to do is keep cycling this. I would say that to get the liquids into the rotor, I've got a small vacuum chamber, so what I do is I put the liquid in the vacuum chamber and put the rotor in the liquid, close the vacuum chamber, pump out the air, leave it for about 15-20 minutes, and that causes the liquid to get drawn into the rotor, and then I flush it out with the alcohol. You can see although the acetone doesn't seem to be doing that much, when I flush it out I'm getting a lot of debris and muck and whatever this is coming out of it. Without the vacuum chamber it did nothing at all, this just stayed clear. So what I'll do is I'll keep cycling this, keep heating and cooling, and hopefully I can break down the conductive layer completely and hopefully recover this rotor if it hasn't done any real damage to it. I would say that if I try reversing the current on this I get about 8 or 9 microamps, so it's very strange. It's acting like a diode, but obviously it's not supposed to. So I'll keep doing this and see how low I can get the current to go, and if I can get it low enough I'll then try ramping up the voltage, do some proper leakage tests and see if this is safe to use. Okay, so several hours later and probably 8 or 9 cycles I've put through this now, and does seem to be having some effect. It is breaking down, or does seem to have mostly broken down whatever was causing the issue. I don't know the chemistry behind this, I don't really know exactly what was going on, but what seemed to happen was whatever the material is that was being used to insulate this, it seems to have absorbed moisture or some chemical, and it's reacted and it's started to act a bit like a semiconductor when it's in contact with the steel of the rotor. And so I've cleaned out some of the pieces that were slid in to hold the windings in place, and I've kept flushing it out. I used the vacuum chamber to draw solvent in and then pass current through it, and I'm trying to break down whatever the layer is that was causing the conductive path. So I've got this set up the same. I'll just move the camera across so you can see the supplies. These are both set to around 60 volts, 61 volts, and then we have the current meter up there that's in series. So it's giving me about 120 volts across the rotor. So we'll turn the two supplies on. So we've now put about 120 volts across the rotor, and if we look at the current meter, before we were getting, in fact I was originally getting up around 70 or 80 milliamps, and as you can see we're now getting just a few microamps. I'll just put the camera down. So I'll turn the power supplies off. So they're now off. You can see that we're just getting kind of noise now on the leads. I'll turn the supplies back on, and it's now fairly consistent. I'll run this through 6 or 7 more times, and then I'll do a full pat test on the rotor and then on the assembled motor and see if this has resolved the issue. I was really aiming to get the current under 20 microamps, which we have now done. What I will do is just try reversing the current to make sure that I haven't introduced something else. So I'm just going to turn the supplies off and swap the two leads around. And now I'll turn the supplies back on. And you can see still a slight difference in the two polarities. It'd be nice to get them both the same, so I know that whatever's there is completely gone. I'll just swap the leads back and make sure that the effect is repeatable. Okay, I'll turn the supplies back on. So we're getting probably 7 or 8 microamps difference between the two, but as I said I was getting pretty much the same in the reverse direction of just 6 or 7 microamps, and about 70-80 milliamps in this direction. So it has greatly improved what we're seeing in terms of the leakage current. I'll just move the camera down so you can see that it's still connected up the same. All the brown, by the way, is just me using the hot air gun on the rotor to heat and cool it. So as I say, I'll do this a few more times and put it back through the solvents, and then I'll do a final full heat dry cycle using the vacuum chamber just to make sure there's no moisture in there. And if the current stays low, the leakage current, then what I'll do is lacquer the rotor, partly to keep the windings in place, because I have taken out the little infills. I don't think the windings will go anywhere now. They seem to have been fairly set in whatever this black material is, but it's mainly to make sure that the material, whatever it is, can't absorb any more moisture or whatever it was absorbing, and to keep the rotor stable so we don't end up with the same situation again. Okay, I finished with the rotor as far as trying to clean it and test it is concerned. I've given it a full high voltage pat test, and it now seems fine. I'm not really getting any appreciable leakage. There's a little bit, just a microamp or two, and there's about now 2 microamps difference in the two polarities, but you would tend to see a small difference anyway, but we're not seeing the several orders of magnitude difference that we were seeing before. The difference was 2 or 3 microamps in one direction and 80 milliamps in the other direction. So it appears that there was some contaminant in the material, or some some buildup of oxide layer on the metallic parts of the rotor, and cycling through solvents and heat and cool cycles seems to have cleaned that up. One thing I thought I'd show before I finish this video, the next thing I'm going to do is reassemble the motor, run it again for several hours, and then do a full pat test on it to make sure this is a permanent fix. I'll also put some lacquer onto the rotor. I'll mask off the shaft and the commutator and then lacquer the rest, just to make sure that it's sealed, and then hopefully this won't reoccur. But just one interesting thing, what I've got in here is this is denatured alcohol. I was using this to flush out the rotor, so I was soaking the rotor in a solvent, and then I would use a vacuum chamber to try and dry it, and then in a vacuum chamber I would immerse it in the alcohol, and that draws the alcohol in, and then I'd flush it a few times. So this black gunk is essentially what I was flushing out. But one thing that's interesting is if we take some of the alcohol that's clean, we should get quite a high resistance, and we can see we're getting up near 100 mega ohms. And this is out of the same bottle, but if I put the probes into this, you can see it's quite a low resistance. So whatever's in there, it does conduct, or it's causing conduction within the alcohol. It's supposed to be the insulation, of course, so it should be a fairly good insulator, but whatever it is that we've flushed out does seem to conduct electricity fairly well, even in a fairly light suspension. It's giving us quite a good conductivity within the liquid. So something strange going on with whatever this material is. If you know what this is, if you know the chemistry behind this, then please leave a comment. I'm sure that a lot of people would be interested to learn what's causing this, and how to deal with it more effectively in future. And just a final look at the leakage current. It's sitting up around between 16 and 20 microamps, and I'll turn the supplies off. They're now off, and you can see it's around 10 or 12. There'll be some residual reading there. It's just noise that's being picked up within the lab. I'll turn the supply back on, and you can see we're back up to 17, 18. I'll turn it off one more time. So we're getting maybe 5 microamps, 6 microamps difference between on and off, which is now the same in both directions. So I'm fairly confident that this has dealt with the issue. What I'll do now is I'm going to leave it for 24 hours, rerun this test to make sure it's stable, and what I'll do then is impregnate the rotor with a good lacquer that's going to be absorbed, kind of thin lacquer. I'll soak it in there for maybe half an hour in the vacuum chamber, take it out, let it drain, back in the oven, let it dry, and then I'll rerun this test yet again and make sure that this is a permanent fix, but it's certainly looking promising at the moment.